Next up, valid parentheses, LeetCode number 20. I'm actually a big fan of this question, and I think other people are too. It's important to do because it's a very popular question, and it leverages an important data structure, the stack. Here's the definition, valid parentheses. Given a string that contains just the characters opening and closing parentheses, opening and closing curly brackets, and opening and closing brackets, determine if the input string is valid. We measure valid by open brackets being closed by the same type of bracket and open brackets being closed in the correct order. Note that an empty string is also considered valid. With all that in mind, let's step through a few examples. Here's a simple one, just an opening and closing parentheses. Obviously this one is valid or true. The next one, we have a set of one each, all neatly opened and closed in the right order. So this one is valid or true. Here's a simple false example and a more complex false example where there are nested parentheses and they're not closed in the proper order. So to formalize our inputs and outputs, our input is just going to be a string comprised of these 6 possible different characters. Our output will be a Boolean true or false, telling us whether the string is valid or not. The definition outlined our edge case for us, which is the empty string input, and in that case, we just want to return true. Let's also, just to be safe, say that there's going to be no weird characters that are not one of these 6 characters. We can begin to build our approach by taking an example and noticing some universal properties within what we want to do. Notice every time we close a parenthesis, for it to be a valid closure, it has to be the same type as the parenthesis we most recently opened. For a simple example, obviously, our parentheses have to match, but even if we get to a more complex example with multiple nested parentheses, this universal rule of closing the one we most recently opened holds true. This technique of breaking a problem into a smaller subproblem is called chunking. So we can have a huge parentheses string, but whether it's size 1 or size 100, we're just checking if the parenthesis we closed matches the one we most recently opened over and over again. In fact, this simple rule is our entire problem. If you can start thinking of your programs in simple chunks like this, complex problems become a lot more simple. It's also why starting with the simplest possible example is a good rule of thumb. And we've already been doing this a ton by breaking down a loop into its iteration slices, or chunks, and generalizing that behavior to make assumptions about the problem as a whole. Anyway, how do we implement this rule we just discovered? That is closing the most recent opening parenthesis. Like other problems, we're going to want to move from left to right through our string. On top of that, we'll always want to keep track of the last parenthesis we saw so we can close it. This works, but what if we have 3 opening parentheses in a row, then 3 closing parentheses in a row? If we're only storing the last opening parenthesis we saw, we would lose reference to the other 2. If you see where I'm going with this, we're going to have to store this data in a data structure called a stack.
You may not be aware of this, but we've already been using a stack a lot.
Because a stack is simply an array, but it's actually a more specific array in which we have to add and remove from it in a particular order. And that order is last in, first out. So like a stack of cafeteria trays or t-shirts, whichever one you add to the top is also the first one you would remove. The way arrays are built in JavaScript and lists are built in Python most closely resembles a stack. That's because the most common methods are either pushing or appending, that is adding an item to the end, and popping, which is removing that item from the end. So we can call these push and pop methods the stack API. Stacks are used a ton in programming, for everything from the call stack, which keeps track of which functions we've called and the order we have to return them in, to algorithms we'll get to like DFS or depth first search. But in this example, we're just going to use a stack in a very simple way. If we walk through an example like this with 3 left parentheses and 3 right parentheses, as we see an opening parenthesis, we can just push it onto the stack, saving it for later. Then, once we see a closing parenthesis, we can pop off from the top of the stack and see if it matches. So this will enforce that universal matching rule that we discovered. If the rule is ever broken, we could just return false. And if we successfully check all our parentheses, we can return true. So that's actually everything we need to solve this one. So here's the pseudocode, and you can pause the video here if you'd like to give it a shot. Alright, ready to go with our single argument S for our input string. And the string will only be comprised of opening and closing parentheses of the 3 different types. Now we know we're going to have to use a stack to keep track of our opening parentheses, so let's declare the variable stack as an empty array. Now we want to check one character at a time and do not need an index. So what we can use is a for of loop here. For char of S, which will pull each character into the variable char. Now there's a couple different ways we could write this, adding to and pulling out of the stack. The first way is a little bit more wordy, but it's more clear. So we'll do that way first, and then we'll optimize it later. So what I'll do for every character is check if it's an opening or a closing parentheses. So I'm going to manually do this check to see if it matches any of the opening character types. And I'll do this by just writing everything out. So if char is equal to opening parenthesis, or char is equal to opening bracket, or char is equal to opening curly bracket. Well, if that's the case, I know we're going to want to add it to our stack. So stack push character. Now, if I hit an else block, I can draw the conclusion that this is instead a closing parenthesis. And in that case, we want to see if it matches the last opening character we pushed onto the stack. But we have to be a bit careful here, because what if our first character is a closing parenthesis? Well, we'd hit the else block, but we'd have an empty stack. So before I pull an item out of the stack, I have to check to see if the stack is empty. So I'll do if stack length is equal to 0. Well, if that's the case, I want to return false, because we should never have an empty stack and a closing parenthesis. So we can say that would instantly invalidate the string. Otherwise, I can pull out the last item from the stack. So I'm just going to save it any variable last and do that with the pop method, removing one from the top or the end of our stack. Last in, first out. Then I'll have to check this last opening character against the current character I'm looking at, which is char, the closing character. So let's look at it this way. If last equals opening parenthesis and char is not equal to closing parenthesis, then I can return false, because we do want this to be true. Then I'll do a couple else blocks to just manually check all the parenthesis types. So these if blocks are just disqualifiers. So if any of these are not true, then we're returning false. And I know this is starting to look like an eyesore, but hopefully you're still with me. Now, if none of these disqualifiers get hit, then our opening parenthesis does match our closing parenthesis. So if essentially we make it to the bottom, jumping outside of the loop, we're going to want to return true for successful. But before that, we also have to consider, what if we still have items in our stack that is opening parentheses that never got closed? Well, that would mean it's also invalid. So let's check if stack still has length or items in it and return false as well. Otherwise, we're free and clear. We finally passed all our conditions and we can return true. So if we look at this code, we have a lot of repeating code here and a lot of redundant checks. So there is a great way to optimize this, and it's by defining an object that matches every parenthesis to its counterpart. And this will do a few things to reduce this repetition. So let me show you how to do that. I'll define a variable called pairs and set it to an empty object. Now inside that object, I'll just define each parenthesis as the key and its counterpart as the value. And I'll do that for the bracket as well as the curly bracket. With this done, I can replace this code block with the nicer syntax to check a key's existence in an object. So I can just do if character in pairs. That is, checking all the keys. So if it's one of these keys, then this will be true. Now, instead of checking each parenthesis manually for its counterpart, we can replace all this code by just doing a lookup in this object. Keep in mind, last is the opening that we pushed onto the stack. And car, assuming that we're in the else block, would be the closing parenthesis. So we want to check the object. If pairs last, remember the opening is the key. If that is not equal to the current car we're looking at, well, if that is the case, then we want to return false. So a single disqualifier by doing a lookup in the table, going from all this code down to this one line. So overall, a pretty nice optimization that only costs us a constant amount of extra space. Let's talk Big O. Looking at time complexity, we have this one loop that's just checking each character one time. So it's a pretty straightforward linear time complexity, O of n. No surprises here. Looking at space, we do need space for our stack, which in the worst case could be O of n because all our items could be opening parentheses. So our space complexity is going to be O of n linear. With this problem done, you should be a bit more familiar with the stack data structure. We'll be using the stack in interesting ways in future videos. Stacks are used for everything from the call stack and recursion to other algorithms like depth first search. So the more practice you can get with the stack, the better.